Right now, somewhere in the universe, two neutron stars are about to collide. Each one weighs more than our sun, but measures only 12 miles across. When they crash, they will release more energy in 1 second than our galaxy produces in an entire year. But this kilonova explosion is just the beginning. We are about to witness stellar corpses that fire gamma-ray beams across billions of light years, black holes that devour entire solar systems, and cosmic events so violent they could reshape reality itself. If you want to see how powerful the universe really gets, hit that like button and subscribe. Prepare yourselves. We begin. A bolt of lightning tears through the sky above your head, carrying 5 billion volts of electricity. This single flash heats the air to 50,000 degrees Fahrenheit. That is 5 times hotter than the surface of the sun. The thunder you hear afterward is actually a sonic boom, created when superheated air expands faster than sound itself. In less than 1,000th of a second, this electrical discharge has unleashed enough energy to power a typical American home for an entire month. But how does nature create such incredible power? Picture the atmosphere as a massive battery that is constantly charging itself. Storm clouds act like towering electrical generators, with ice particles and water droplets colliding billions of times. Each collision strips away tiny electrical charges, separating positive and negative particles like a cosmic game of static electricity. The top of the cloud becomes positively charged, while the bottom turns negative. Meanwhile, the ground below develops a positive charge that grows stronger as the storm builds overhead. The electrical difference between cloud and ground creates an invisible pathway through the air. Think of it like stretching a rubber band tighter and tighter until it finally snaps. When the electrical tension becomes too great, nature finds the path of least resistance. The lightning bolt we see is actually electricity racing both ways at once. A nearly invisible leader stroke creeps down from the cloud, testing different paths through the air. When it gets close enough to the ground, a return stroke rockets upward at 1/3 the speed of light. This return stroke is what creates the brilliant flash we see and carries most of the electrical current. Some lightning bolts stretch over 100 miles long. Others strike the same spot multiple times in rapid succession, creating the flickering effect we sometimes observe. The most powerful lightning ever recorded carried over 300,000 amperes of current. To put that in perspective, a typical household electrical outlet delivers just 15 amperes. Lightning kills about 25 people in America every year and starts thousands of wildfires. But it also serves a crucial purpose for life on Earth. Every lightning bolt creates nitrogen compounds that fertilize soil when carried down by rain. Without lightning, many plants would lack the nutrients they need to survive. In some parts of the world, lightning strikes the ground over 200 times per minute during peak storm season. Lake Maracaibo in Venezuela experiences lightning almost 300 nights per year, making it the most electrically active place on our planet. Yet, for all its devastating power, lightning represents just the beginning of nature's electrical fury. The energy in one lightning bolt seems enormous, until you consider what happens when our sun decides to unleash its own version of electrical violence. But those solar storms operate on a scale that makes earthly lightning look like a tiny spark. The most powerful weapon humanity ever created turned sand into glass across an area larger than Manhattan. When the Tsar Bomba detonated over the Soviet Arctic in 1961, it released the energy equivalent of 50 million tons of dynamite. The fireball alone measured over 2 miles across and could be seen from 600 miles away. The mushroom cloud rose 39 miles into the atmosphere, 7 times higher than Mount Everest. Windows shattered in buildings over 500 miles from ground zero. But what makes nuclear weapons so catastrophically powerful compared to conventional explosives? The answer lies in the very heart of matter itself. Traditional explosives work by breaking chemical bonds between atoms, like snapping the connections in a complex house of cards. Nuclear weapons do something far more fundamental. They actually split atoms apart or fuse them together, releasing the enormous energy that holds the nucleus together. Think of an atom like a tightly wound spring that has been compressed for billions of years. When you split certain heavy atoms like uranium, or plutonium, that spring suddenly uncoils with incredible force. In nuclear fission, one atom splits into two smaller pieces, releasing neutrons that crash into nearby atoms and split them as well. This creates a chain reaction that spreads through the nuclear material in microseconds. The process follows Einstein's famous equation that energy equals mass times the speed of light squared. Since the speed of light is enormous, even tiny amounts of matter convert into staggering quantities of energy. A single pound of uranium contains as much energy as 1,400 tons of coal. During the first nuclear test in New Mexico, scientists were not completely certain the chain reaction would stop. Some worried it might ignite the entire atmosphere and destroy all life on Earth. Fortunately, their calculations proved correct, but the explosive yield still exceeded their predictions by 30%. The heat at the center of a nuclear explosion reaches 100 million degrees Fahrenheit. That is 6 times hotter than the core of the sun. The initial gamma radiation moves outward at the speed of light, followed by an intense thermal pulse that can cause third-degree burns 15 miles away. Then comes the blast wave, a wall of compressed air traveling faster than the speed of sound. Modern nuclear weapons use a two-stage design, where a small fission bomb triggers an even more powerful fusion reaction. These hydrogen bombs force light atoms like deuterium and tritium to combine into heavier elements, releasing even more energy than fission alone. The largest weapon ever designed by the United States had a planned yield of 25 megatons, but was never tested at full power. However, nuclear weapons pale in comparison to the explosions happening naturally throughout our solar system every single day. Our sun converts 4 million tons of matter into pure energy every second through nuclear fusion. But even our star's constant nuclear fire seems gentle when you witness what happens when solar plasma decides to break free and hurtle toward Earth at millions of miles per hour. Beneath Yellowstone National Park, a chamber of molten rock the size of Los Angeles sits just 5 miles below your feet. This supervolcano has erupted 3 times in the past 2 million years, and each explosion was thousands of times more powerful than any nuclear weapon. The last eruption, 640,000 years ago, ejected enough ash and debris to bury the entire state of Texas under 3 feet of volcanic material. The ash clouds circled the globe and blocked sunlight for years, triggering a volcanic winter that changed Earth's climate. Volcanic eruptions happen when the incredible pressure of molten rock called magma finally overcomes the solid crust above it. Picture the Earth like a pressure cooker filled with liquid rock heated to over 2,000 degrees Fahrenheit. Just as steam builds pressure in a pot until the lid blows off, magma finds weak points in the rocky shells surrounding our planet and explodes toward the surface. The most explosive eruptions occur when gas-filled magma encounters water, or when the magma itself contains high levels of dissolved gases. As the molten rock rises toward the surface, decreasing pressure causes these gases to expand rapidly, like opening a shaken bottle of soda. The result is a violent explosion that can launch rocks the size of cars over 20 miles into the air. Mount Vesuvius famously buried the Roman cities of Pompeii and Herculaneum in 79 AD, preserving them under layers of ash and pumice. But that eruption was relatively small compared to what volcanoes can really do. The 1815 eruption of Mount Tambora in Indonesia killed over 70,000 people and caused global climate chaos. Crops failed worldwide, leading to famine, disease, and social unrest across Europe and North America. The most powerful volcanic eruption in recorded history happened in 1883 when Krakatoa exploded with the force of 200 megatons of TNT. The sound of the explosion was heard 3,000 miles away, and the pressure wave circled the Earth 7 times. Tsunamis generated by the blast reached 130 feet high and killed over 36,000 people across Indonesia. But terrestrial volcanoes seem almost gentle compared to the volcanic activity we observe on other worlds. Io. One of Jupiter's moons experiences volcanic eruptions that shoot lava fountains over 250 miles high, that is 50 times higher than any eruption ever recorded on Earth. The low gravity and thin atmosphere allow volcanic plumes to reach incredible heights that would be impossible on our planet. Some volcanic eruptions on Io release sulfur dioxide at temperatures exceeding 3,000 degrees Fahrenheit. These alien volcanoes are powered not by internal heat, like Earth's volcanoes, but by the constant gravitational squeezing from Jupiter and its other large moons. This tidal heating keeps Io's interior molten and drives continuous volcanic activity across its entire surface. Yet even the most violent volcanic eruptions we have observed still cannot match the raw power that our sun releases when it experiences a really bad day and decides to hurl billion-ton clouds of plasma directly at our planet. A twisted loop of magnetic field on the sun's surface suddenly snaps like a rubber band and releases the energy of 1 billion hydrogen bombs. This solar flare erupts from a region called a sunspot, where magnetic field lines become tangled and stretched until they can no longer hold their shape. When these magnetic structures finally break and reconnect, they launch high-energy particles and radiation across the solar system at speeds approaching the velocity of light itself. The largest solar flares ever recorded belong to a category scientist called X-class events. Think of the sun's magnetic field like invisible rubber bands stretched across its surface. During periods of high solar activity, these magnetic field lines twist and tangle as the sun rotates. Different parts of our star spin at different speeds, with the equator completing one rotation every 25 days while the poles take 35 days. This uneven rotation winds up the magnetic field like a spring until something has to give. When magnetic field lines with opposite polarities get close enough, they suddenly snap together in a process called magnetic reconnection. The energy stored in these magnetic fields converts instantly into kinetic energy, heating plasma to temperatures exceeding 20 million degrees Fahrenheit. Solar flares accelerate particles to nearly the speed of light and send them racing across 93 million miles of space toward Earth. The most powerful flare ever directly observed occurred in 2003 and was later classified as an X-28 event. This monster flare saturated the sensors designed to measure it, meaning its true intensity was probably much higher than we could accurately record. When solar flare particles reach Earth, they interact with our planet's magnetic field and atmosphere in spectacular ways. The charged particles follow magnetic field lines toward the poles where they collide with oxygen and nitrogen molecules in the upper atmosphere. These collisions create the beautiful auroras we see dancing across the sky in green, red, and purple curtains of light. But solar flares can also cause serious problems for our technology-dependent civilization. The high-energy particles disrupt radio communications, damage satellites, and can even affect power grids on Earth's surface. In 1859, a massive solar storm called the Carrington event caused telegraph systems worldwide to fail. Some telegraph operators received electric shocks, and telegraph paper caught fire in multiple locations. If a Carrington-level event happened today, it could cause trillions of dollars in damage to our electronic infrastructure. GPS systems would fail, internet communications would be disrupted, and power grids could collapse across entire continents. Airlines would have to ground flights to protect passengers from radiation exposure, and astronauts on the International Space Station would need to take shelter in specially shielded compartments. Solar flares typically last only minutes or hours, but their effects can persist for days as charged particles continue streaming through the solar system. However, these individual flares are nothing compared to what happens when Sun decides to launch an entire chunk of its outer atmosphere directly toward Earth at speeds exceeding 1 million miles per hour. A billion tons of superheated plasma tears away from the sun and begins racing toward Earth at over 2 million miles per hour. This coronal mass ejection carries the magnetic field strength of 1 million Earth magnets and enough energy to power the United States for 20,000 years. Unlike the brief bursts of solar flares, these massive chunks of the sun's atmosphere can stretch across distances larger than the orbit of Mercury. When they slam into Earth's magnetic field, they can compress it so violently that our protective magnetic bubble temporarily collapses on the side facing the sun. Coronal mass ejections happen when enormous loops of magnetic field lines extending far above the sun's surface become unstable and snap. Picture a soap bubble forming and then suddenly bursting, except This bubble is made of million-degree plasma and measures larger than Jupiter. The magnetic field lines act like invisible cages holding vast amounts of solar material in the sun's corona. The wispy outer atmosphere we can see during a total solar eclipse. When these magnetic cages break open, they launch billions of tons of charged particles into space in all directions. The fastest coronal mass ejections can travel at speeds up to 9 million miles per hour, crossing the 93 million mile gap between Sun and Earth in just 15 hours. Most take 2 to 4 days to make the journey, giving us some warning when space weather monitoring satellites detect them leaving the Sun. The 1989 Quebec blackout demonstrated how dangerous these solar storms can be for modern civilization. A moderate coronal mass ejection hit Earth and induced electrical currents in power transmission lines across eastern Canada. The power grid collapsed within 90 seconds, leaving 6 million people without electricity for 9 hours during a cold March night. Transformers overloaded and exploded, causing damage that took months to repair. But Quebec was just a preview of what a truly massive coronal mass ejection could do. The July 2012 event missed Earth by just 9 days in our orbit around the Sun. If it had hit our planet, scientists estimate it would have caused over $2 trillion in damage and taken 4 to 10 years to fully repair the electrical infrastructure. We came closer to a technological apocalypse than most people realize. Coronal mass ejections also create some of the most beautiful auroras ever witnessed. In 1859, the Great Geomagnetic Storm caused auroras so bright that people could read newspapers by their light. The northern lights appeared as far south as the Caribbean, and the southern lights were visible from Rome. Telegraph systems worldwide failed, but some operators discovered they could disconnect their power sources and send messages using only the electricity induced by the geomagnetic storm. These solar storms affect more than just Earth. Coronal mass ejections sweep across the entire solar system, disrupting the magnetic environments of other planets and their moons. They can strip away parts of planetary atmospheres and even influence the formation of comet tails as they pass by these icy visitors from the outer solar system. Yet, coronal mass ejections represent just one way that stars can violently expel material into space. And our sun is actually quite gentle compared to other stellar winds that blow through the galaxy. Some stars blast material into space with such incredible force that they lose the mass of our entire Earth every single year. These stellar winds are not gentle breezes like the solar wind from our sun, which moves at a relatively modest 300 miles per second. The most massive stars drive winds that race away from their surfaces at speeds exceeding 4,000 miles per second. That is fast enough to travel from New York to Los Angeles in 30 seconds. Wolf-Rayet stars represent some of the most extreme wind machines in the universe. These stellar monsters are so hot and luminous that their own radiation pressure literally blows their outer layers into space. And think of standing next to a massive fan that is so powerful, it strips the clothes right off your body. Except in this case, the fan is powered by nuclear fusion. And the clothes being stripped away are entire atmospheric layers containing more mass than Jupiter. The winds from these dying giants create spectacular nebulae as they collide with previously ejected material or sweep up gas and dust from the surrounding interstellar medium. The Ring Nebula, visible through small telescopes in the constellation Lyra, formed when a central star expelled its outer atmosphere in a series of powerful stellar winds over thousands of years. Blue supergiant stars drive some of the fastest stellar winds ever observed. These stellar behemoths can be 30 times more massive than our sun and burn through their nuclear fuels so rapidly that they live only a few million years. Their intense radiation heats their outer atmospheres to temperatures exceeding 80,000 degrees Fahrenheit, hot enough to ionize heavy elements and accelerate them to incredible velocities. Some stellar winds are so powerful they actually shape the structure of entire star-forming regions. Young massive stars blow away the gas and dust that originally surrounded them, creating vast cavities in space that can stretch for dozens of light years. These stellar wind bubbles eventually collide with each other, triggering the formation of new stars in the compressed material at their boundaries. The fastest stellar winds on record come from central stars of planetary nebula, reaching speeds up to 2,500 miles per second. These are the exposed cores of dying stars that have already shed most of their outer layers. With their nuclear fires nearly extinguished, they rely on their remaining heat to drive these final desperate winds that clear away the last traces of their former atmospheres. Binary star systems can create even more dramatic wind interactions when stellar winds from two stars collide in the space between them. These wind collision zones heat material to millions of degrees and generate high-energy X-rays that astronomers can detect across vast distances. Some of these colliding wind systems create spiral shock patterns as the two stars orbit each other, leaving beautiful traces of their cosmic dance. However, stellar winds seem almost calm when you consider what happens when entire worlds crash into each other, with enough force to literally vaporize solid rock and create new moons from the debris of planetary destruction. 4.5 billion years ago, a Mars-sized planet slammed into the early Earth with such devastating force that it melted both worlds completely and ejected enough molten rock to form our moon. This collision, called the Giant Impact Hypothesis, released more energy than all the nuclear weapons ever built, combined by a factor of several billion. The impact heated Earth's surface to over 4,000 degrees Fahrenheit, hot enough to vaporize rock and create a global ocean of molten lava, hundreds of miles deep. The collision was so violent that it knocked Earth's rotation axis 23.5 degrees off vertical, giving us the seasons we experience today. Planetary collisions happen when the gravitational dance of worlds goes wrong. During the early formation of our solar system, countless rocky bodies, called planetesimals, crashed into each other repeatedly. Most collisions resulted in the smaller object being absorbed by the larger one, gradually building up the planets we see today. But sometimes two similarly sized objects would meet head-on with catastrophic results. Picture two cars racing toward each other at 60,000 miles per hour, except these cars are made of solid rock, and each one weighs as much as an entire planet. The collision energy depends on both the masses involved and their relative velocity. When objects moving in opposite directions around the Sun collide, their combined orbital speeds can reach over 100,000 miles per hour at the moment of impact. The aftermath of major planetary collisions can reshape entire solar systems. Computer simulations show that when two Earth-sized planets collide, they can completely merge into a single larger world, shatter into countless fragments that later reassemble, or even bounce off each other and continue on separate paths, depending on the angle and speed of impact. We have discovered evidence of ancient planetary collisions throughout our solar system. Mercury's unusually large iron core suggests it may have lost most of its rocky mantle in a massive impact early in its history. Uranus rotates on its side, likely due to a collision that knocked it over. The asteroid belt between Mars and Jupiter might be the shattered remains of a planet that never quite formed to disruptive encounters with other worlds. Some planetary collisions create debris that goes on to form spectacular ring systems. Saturn's magnificent rings may have formed when a moon or large asteroid was torn apart by tidal forces as it ventured too close to the giant planet. The debris spread out into a thin disk that we now see reflecting sunlight across hundreds of thousands of miles. Modern telescopes have detected the heat signatures of recent planetary collisions around other stars. These collisions generate so much thermal energy that they glow brightly in infrared light for years after the impact. Astronomers have observed several young star systems where massive collisions appear to be happening right now, giving us real-time glimpses of the violent process that shaped our own solar system. But even the most energetic planetary collisions pale in comparison to what happens when gravity itself becomes so concentrated that it creates objects too massive to ignite as stars, yet too small to shine with nuclear fire. A cloud of gas and dust 30 times more massive than Jupiter begins collapsing under its own gravity, heating up to millions of degrees as it falls inward on itself. This brown dwarf formation releases gravitational energy equivalent to the sun's total output for over 10 million years. Unlike planets that form gradually through the accumulation of solid material, Brown dwarfs collapse catastrophically in a process that takes less than 100,000 years. The gravitational potential energy of all that infalling matter converts to heat and light, creating some of the most luminous objects in the galaxy during their formation phase. Brown dwarfs occupy a strange middle ground between planets and stars. They form the same way stars do, through the gravitational collapse of gas clouds, but they never accumulate enough mass to sustain hydrogen fusion in their cores. Think of them as stellar failures that came close to becoming real stars, but fell just short of the minimum mass requirement. The formation process begins when a particularly dense region in a molecular cloud starts attracting surrounding material through gravitational attraction. As more gas falls toward the center, the growing proto-brown dwarf heats up due to the conversion of gravitational potential energy into thermal energy. This is the same process that heats a ball when you drop it, except scaled up to cosmic proportions with unimaginable amounts of mass involved. During the collapse phase, temperatures in the core can reach 15 million degrees Fahrenheit. This is hot enough to briefly ignite deuterium fusion, a process that burns the small amount of heavy hydrogen present in the original gas cloud. However, deuterium is extremely rare, and this fusion phase lasts only a few million years before the fuel runs out and the brown dwarf begins its long cooling process. The most massive brown dwarfs can sustain lithium fusion for a somewhat longer period, but this nuclear burning is much less efficient than the hydrogen fusion that powers true stars. Eventually, all brown dwarfs exhaust their limited nuclear fuel and become gradually cooling balls of hot gas that will fade away over trillions of years. Some brown dwarfs form in binary systems with normal stars, creating exotic partnerships where a failed star orbits a successful one. In these systems, the brown dwarf can sometimes steal material from its stellar companion, briefly reigniting nuclear fusion on its surface in spectacular thermonuclear explosions that can outshine entire galaxies for short periods. The formation of brown dwarfs also creates powerful jets of material that stream away from their poles at speeds exceeding 600 miles per second. These jets form when magnetic fields channel infalling material into narrow beams that extend for light years into space. The jets carve out vast cavities in the surrounding interstellar medium and can trigger the formation of new stars when they collide with nearby gas clouds. Recent observations have discovered brown dwarfs that are still in the process of forming, allowing astronomers to study this violent gravitational collapse in real time. These young objects are among the brightest infrared sources in the sky, shining with the heat generated by their ongoing gravitational contraction. However, brown dwarf formation seems almost gentle compared to what happens when truly massive stars reach the end of their lives and begin expanding to sizes that dwarf our entire solar system. A dying star swells to over 1,000 times its original size, growing so large that if it replaced our sun, its surface would extend beyond the orbit of Jupiter. This red giant expansion happens when a star exhausts the hydrogen fuel in its core and begins burning heavier elements in shells around a growing helium center. The outer atmosphere becomes unstable and begins puffing away from the star in massive thermal pulses that can eject the mass of Earth every few thousand years. Each pulse releases energy equivalent to our sun's total output for 10,000 years. The expansion process transforms stars in ways that seem almost impossible. Imagine a basketball suddenly inflating to the size of a football stadium while losing most of its weight. The surface gravity of a red giant becomes so weak that material can easily escape into space, creating the spectacular planetary nebulae we observe throughout the galaxy. Betelgeuse, the red supergiant that forms the shoulder of Orion, demonstrates just how enormous these dying stars can become. If we could place Betelgeuse at the center of our solar system, its surface would swallow Mercury, Venus, Earth, Mars, and possibly even Jupiter. The star's diameter measures over 400 million miles, large enough that light takes 20 minutes to travel from one side to the other. Red giant expansion occurs in distinct phases as stars burn through progressively heavier elements in their cores. First, they exhaust hydrogen and begin fusing helium into carbon and oxygen. When the helium runs out, more massive stars continue burning carbon into neon, then neon into silicon, and finally silicon into iron. Each phase burns faster and more violently than the previous one, causing the star's outer layers to expand further and become increasingly unstable. The most massive red giants experience something called the helium flash, where helium fusion ignites explosively in the star's core. This thermonuclear detonation releases more energy in a few seconds than our sun produces in 100 million years. The flash heats the core to over 300 million degrees and can cause the entire star to temporarily brighten and change color as shockwaves propagate through its interior. Some red giants pulsate regularly as they struggle to maintain stability during their death throes. These variable stars can change brightness by factors of thousands as their outer atmospheres alternately expand and contract. The pulsations follow complex patterns that depend on the star's mass, composition, and evolutionary stage. When red giants finally shed their outer atmospheres completely, they leave behind hot white dwarf cores that slowly cool over billions of years. The ejected material forms beautiful planetary nebulae that can remain visible for tens of thousands of years as the central white dwarf ionizes the surrounding gas with its intense ultraviolet radiation. But the gentle expansion and mass loss of red giants seems almost peaceful when compared to what happens when some of these stellar remnants suddenly detonate with the explosive power to outshine entire galaxies and create shockwaves that propagate across interstellar space for millions of years. A white dwarf star quietly accumulates material from its companion for millions of years until it suddenly explodes with the force of 5 billion suns. This type ES supernova tears the white dwarf completely apart in a thermonuclear detonation that converts nearly half the star's mass into radioactive nickel in less than 10 seconds. The explosion accelerates debris to speeds exceeding 20,000 miles per second and creates a shock wave that will expand for hundreds of thousands of years, heating interstellar gas to temperatures exceeding 50 million degrees Fahrenheit. White dwarf explosions happen in binary star systems, where a dense stellar remnant slowly steals material from a normal star companion. Picture a cosmic vampire that feeds on its partner for millions of years, growing more massive and unstable with each meal. The white dwarf's intense gravity pulls hydrogen from the companion star's outer atmosphere, forming an accretion disk of superheated gas that spirals inward and eventually settles on the white dwarf's surface. As the white dwarf accumulates more mass, its core temperature and density increase dramatically. The stellar remnant is essentially a ball of carbon and oxygen held up by electron degeneracy pressure, a quantum mechanical effect that prevents matter from collapsing further. But there is a limit to how much mass this quantum support can handle. When the white dwarf reaches approximately 1.4 times the mass of our sun, called the Chandrasekhar limit, the electron degeneracy pressure can no longer resist gravitational collapse. The entire star begins falling inward, but instead of forming a neutron star, the carbon and oxygen nuclei become hot and dense enough to undergo explosive fusion. The nuclear burning front spreads through the white dwarf in a runaway chain reaction that takes only seconds to consume the entire star. Unlike the controlled fusion in normal stellar cores, this process is completely unstable. Think of the difference between a candle burning steadily and a stick of dynamite exploding. The white dwarf has no way to regulate the fusion rate, so the reaction accelerates until it completely destroys the star. Type 1a supernovas are so consistent in their peak brightness that astronomers use them as standard candles to measure cosmic distances, because all white dwarfs explode at nearly the same mass. They release similar amounts of energy and reach comparable maximum luminosities. These stellar explosions can be seen from billions of light years away and have helped us discover that the expansion of the universe is accelerating. The explosion creates and disperses many of the heavy elements essential for life, including iron, nickel, and cobalt. The shock waves from white dwarf explosions compress nearby gas clouds and can trigger the formation of new generations of stars. In this way, stellar death enables stellar birth in an ongoing cycle that has continued for billions of years. Some white dwarf explosions occur in systems where the companion star survives the blast, creating a runaway star that races through space at abnormally high velocity. These hypervelocity stars provide evidence of past explosive events and help astronomers understand the complex dynamics of binary stellar evolution. Yet white dwarf explosions, for all their violence, cannot compare to what happens when the most massive stars in the universe finally exhaust their nuclear fuel and collapse into objects so dense that atomic nuclei themselves get crushed out of existence. In less than 1 second, a star 20 times more massive than our Sun collapses from 8,000 miles across down to just 12 miles in diameter. This core collapse compresses matter to densities so extreme that a single teaspoon of neutron star material would weigh 6 billion tons on Earth. The gravitational binding energy released during this collapse exceeds the total energy output of our Sun over its entire 10 billion year lifetime. Most of this energy escapes as neutrinos that pass through matter so easily they could travel through a light year of solid lead without being stopped. Neutron star formation begins when a massive star creates an iron core that can no longer sustain nuclear fusion. Iron nuclei cannot release energy through either fusion or fission, so when the core reaches this point, the star's nuclear fire suddenly dies. Without the outward pressure from fusion reactions, gravity wins the ultimate battle, and the core begins falling inward at speeds approaching 30,000 miles per second. During this catastrophic collapse, atomic nuclei are crushed together with such force that protons and electrons combine to form neutrons. Picture trying to squeeze a basketball down to the size of a marble while keeping all the same mass. The quantum mechanical forces that normally keep atomic nuclei separated are completely overwhelmed by the incredible gravitational pressure. The collapse continues until the neutrons themselves resist further compression through a quantum effect called neutron degeneracy pressure. This is similar to the electron degeneracy pressure that supports white dwarfs, but much stronger. The core rebounds from this compression, creating a shock wave that propagates outward through the star's outer layers and blasts them into space in a spectacular supernova explosion. The resulting neutron star contains more mass than our Sun, compressed into a sphere smaller than Manhattan. The surface gravity is so intense that dropping an object from just 3 feet would accelerate it to over 3,000 miles per hour by the time it hits the ground. Neutron star material is so dense that atomic nuclei are actually dissolved, and the star consists primarily of free neutrons held together by gravitational force. Neutron stars have solid crusts made of atomic nuclei arranged in crystal lattices, but these crusts are incredibly strong. The material is about 10 billion times stronger than steel and can support mountains up to a few inches tall before the extreme gravity flattens them. Starquakes on neutron stars can crack this crust and release more energy than the most powerful earthquakes in Earth's history. The magnetic fields around neutron stars reach strengths of trillions of times stronger than Earth's magnetic field. These fields are so powerful they would be lethal to humans at distances of thousands of miles and can actually alter the structure of atoms themselves. The combination of extreme magnetic fields and rapid rotation creates some of the most exotic physics observed anywhere in the universe. Some neutron stars spin over 700 times per second faster than a kitchen blender. The equatorial surface of these millisecond pulsars moves at nearly 20% the speed of light, creating relativistic effects that warp space and time in their immediate vicinity. But neutron stars are just getting warmed up when it comes to demonstrating the true power of collapsed matter and the incredible forces that extreme gravity can unleash on the cosmos. A spinning neutron star fires beams of radiation across space with such precision that they sweep past Earth like cosmic lighthouse beams, keeping time more accurately than the best atomic clocks. These pulsar emissions carry more power than all the electricity generated by human civilization in the past century. The beams originate from the neutron star's magnetic poles, where charged particles accelerate to nearly the speed of light and emit intense radiation across the entire electromagnetic spectrum, from radio waves to gamma rays. Pulsars form when neutron stars rotate rapidly while maintaining extremely strong magnetic fields. As the star spins, its magnetic field lines get wound up and twisted, creating powerful electric fields that can accelerate particles to incredible energies. Think of the magnetic field like invisible ropes attached to the neutron star's surface that get tangled more and more tightly as the star rotates. The fastest known pulsar spins 716 times per second, completing a full rotation in just 1.4 milliseconds. At this speed, the star's equatorial surface moves at over 100 million miles per hour. The centrifugal force from this rotation is so strong it nearly tears the neutron star apart, but the incredible gravitational binding energy keeps it intact. Pulsar beams are so tightly focused that they can maintain their intensity across thousands of light years. The Crab pulsar formed in a supernova explosion witnessed by Chinese astronomers in 1054 AD, emits pulses that have been detected by radio telescopes on Earth for over 50 years. Each pulse arrives with clockwork precision, deviating by less than 1 part in 10 million from its predicted timing. Some pulsars emit beams that contain more energy per second than our sun produces in an entire year. The most powerful pulsars can accelerate particles to energies exceeding those achieved in our largest particle accelerators by factors of millions. These cosmic accelerators create some of the highest energy particles ever detected, with individual cosmic ray protons carrying enough energy to light a 60-watt bulb for 1,000th of a second. Binary pulsars provide some of the most precise tests of Einstein's theory of general relativity ever conducted. As two neutron stars orbit each other, they lose energy by emitting gravitational waves, causing their orbits to decay at exactly the rate predicted by Einstein's equations. The orbital decay has been measured with such precision that it confirms general relativity to within 1 part in 10 trillion. The discovery of the first pulsar in 1967 initially puzzled astronomers because the signals were so regular, they wondered if they might be artificial transmissions from an extraterrestrial civilization. The signals were even nicknamed LGM-1, standing for Little Green Men. However, the discovery of additional pulsars with different periods quickly confirmed they were natural phenomena. Double pulsar systems, where two pulsars orbit each other, create incredibly complex radiation patterns as their beams sweep across space. These systems will eventually spiral into each other due to gravitational wave emission, creating collisions that generate some of the most violent explosions in the known universe. Yet even the incredible power of pulsar beams pales in comparison to what happens when neutron stars develop magnetic fields so strong they can literally tear apart the fabric of space itself. A magnetar experiences a starquake that cracks its ultra-dense crust and releases more energy in 1/10 of a second than our sun produces in 100,000 years. This magnetar outbursts sends a blast of gamma rays and X-rays across the galaxy with such intensity that it temporarily blinds space-based telescopes and disrupts Earth's upper atmosphere from 26,000 light-years away. The magnetic field around a magnetar is so powerful that it would instantly kill any human within 600 miles by disrupting the bioelectrical processes in their nervous system. Magnetars are neutron stars with magnetic fields that reach strengths of 1 quadrillion times stronger than Earth's magnetic field. To put this in perspective, a magnetar's magnetic field is so intense that it could levitate a paperclip from half the distance to the moon. These magnetic fields are strong enough to distort the shape of atoms themselves, stretching hydrogen atoms into needle-like structures 100 times longer than they are wide. The magnetic field energy stored in a magnetar exceeds the gravitational binding energy that holds the neutron star together. This means the magnetic field is literally strong enough to tear the star apart, and only the incredible density and structural strength of neutron star matter prevents this from happening. When the magnetic field does shift or reconfigure, it can crack the neutron star's crust like an eggshell. Magnetar starquakes are among the most violent seismic events in the universe. The December 27, 2004 outburst from magnetar SGR 180620 briefly became the brightest object ever observed in our galaxy outside of the sun. The initial burst lasted only 0.2 of a second, but released as much energy as our sun produces in 250,000 years. The gamma ray burst from this magnetar was so intense it actually affected Earth's ionosphere, causing it to expand and temporarily disrupting radio communications around the globe. Satellites throughout the solar system detected the blast, and some instruments were completely saturated by the flood of high-energy radiation. If this magnetar had been located just 10 light-years from Earth instead of 50,000 light-years away, the burst would have caused a mass extinction event on our planet. Magnetars can maintain their extreme magnetic fields for only about 10,000 years before the field energy dissipates through electromagnetic radiation and particle emission. During this time, they experience repeated outbursts as internal stresses build up and are suddenly released. Some magnetars have been observed producing dozens of smaller bursts over periods of months or years. The magnetic field lines around magnetars become so twisted and tangled that they can snap and reconnect violently, similar to solar flare, but millions of times more powerful. These magnetic reconnection events accelerate particles to energies that rival the most powerful cosmic ray particles ever detected. The resulting particle beams can extend for light years beyond the magnetar itself. Magnetars represent the most magnetically powerful objects in the known universe, but their incredible outbursts are still just warm-up for the real stellar explosions that can outshine entire galaxies and be seen from billions of light years across the cosmos. A white dwarf star detonates with such incredible force that for several weeks it outshines the combined light of 100 billion stars in its host galaxy. This type E, a supernova, can be seen from over 13 billion light-years away, making it visible across nearly the entire observable universe. The explosion completely destroys the white dwarf, converting approximately 60% of its mass into radioactive isotopes that power the supernova's brightness for months after the initial detonation. Type Ia supernovas occur when white dwarf stars in binary systems accumulate material from their companions until they reach a critical mass threshold. Unlike the gradual explosions we explored earlier, these events happen with shocking suddenness. The white dwarf can remain stable for millions of years, quietly growing more massive, and then explode without warning in a matter of seconds. The thermonuclear detonation begins at a single point inside the white dwarf and spreads through the entire star at speeds exceeding 6,000 miles per second. This burning front converts carbon and oxygen nuclei into iron peak elements through explosive silicon burning. A fusion process so violent it can only occur during the most extreme stellar explosion. The energy release from a type Ia supernova equals approximately 5 billion times 10 to the 43rd Earths, which is more energy than our Sun will produce during its entire 10 billion year main sequence lifetime. To put this in more familiar terms, this single explosion releases as much energy as would be generated by converting the entire mass of Mount Everest directly into pure energy according to Einstein's equation. These supernovas create and disperse many of the heavy elements essential for planet formation and life itself. The explosion forges elements like iron, nickel, cobalt, and zinc that cannot be produced through normal stellar nucleosynthesis. Each type Ia supernova enriches the surrounding interstellar medium with approximately 1 solar mass worth of these crucial heavy elements. The shockwave from the explosion expands at speeds initially exceeding 20,000 miles per second, heating the surrounding interstellar gas to temperatures over 100 million degrees Fahrenheit. This creates a supernova remnant that continues expanding for hundreds of thousands of years, visible as a glowing shell of hot gas that can span dozens of light years across. Type Ia supernovas serve as cosmic distance indicators because they all reach similar peak luminosities. This consistency occurs because the explosions happen when white dwarfs reach approximately the same critical mass known as the Chandra-Sikar limit. Astronomers use this property to measure distances to galaxies billions of light years away, and have discovered that the expansion of the universe is accelerating. Some type Ia explosions are so powerful they can completely unbind their host galaxies, providing enough energy to scatter stars across intergalactic space. The most luminous examples can outshine normal supernovas by factors of 10 or more, reaching peak magnitudes that rival the brightness of entire galaxy clusters. However, even these galaxy outshining explosions seem almost restrained when compared to what happens when the most massive stars in the universe finally reach the end of their lives and collapse in events that make type A supernovas look like. Firecrackers. When a star 50 times more massive than our sun exhausts its nuclear fuel, it collapses and explodes with the energy of 10 billion atomic bombs detonating every second for 10 seconds straight. This core collapse supernova blasts the star's outer layers into space at speeds exceeding 30,000 miles per second, while simultaneously creating a neutron star or black hole in the stellar core. The explosion releases more energy in 10 seconds than our sun will produce over its entire 10 billion year lifetime, with most of this energy carried away by neutrinos that pass through matter as if it barely exists. Core collapse supernovas begin when massive stars create iron cores that can no longer sustain nuclear fusion. Unlike smaller stars that die gradually by shedding their outer layers, these stellar giants face a catastrophic end when their cores reach approximately 1.5 solar masses. At this point, the core temperature exceeds 5 billion degrees, and the iron nuclei begin breaking apart, absorbing energy instead of releasing it. The core collapse happens faster than human comprehension. In less than 1 second, a core measuring 6,000 miles across shrinks down to just 12 miles in diameter. This collapse compresses matter to nuclear density, where atomic nuclei are crushed together until they actually touch each other. The gravitational binding energy released during this collapse exceeds 10 to the 53 ergs, making it one of the most energetic events in the universe. When the collapsing core reaches nuclear density, it suddenly stiffens and rebounds, creating a shockwave that propagates outward through the star's interior. This shockwave starts with enough energy to blast apart the entire star, but it quickly stalls as it encounters the dense material falling inward. For several hours, the outcome hangs in balance as the shockwave struggles to break through the infalling stellar envelope. Neutrinos play a crucial role in reviving the stalled shockwave. The proto-neutron star at the center releases an enormous flood of neutrinos that carry away 99% of the explosion's energy. Even though neutrinos rarely interact with matter, the density behind the shockwave is so extreme that a small fraction of these particles deposit their energy in the stellar material, providing the extra push needed to complete the explosion. The resulting supernova can outshine its entire host galaxy for weeks and remain visible for months as radioactive decay of freshly synthesized elements powers the light curve. These explosions create and disperse elements heavier than iron, including gold, platinum, and uranium. Every atom of gold in your jewelry was forged in the core of an exploding star and blasted into space by a core collapse supernova. The shock waves from these explosions compress nearby gas clouds and trigger the formation of new stars, creating a cycle where stellar death enables stellar birth. Some core collapse supernovas are so powerful they can clear away all the gas in their immediate vicinity, creating vast bubbles in the interstellar medium that persist for millions of years. But core collapse supernovas represent just the beginning of truly cosmic scale violence, as we are about to discover when stellar explosions become so extreme, they challenge our understanding of physics itself. The most massive star in the galaxy collapses and explodes with 100 times more energy than a typical supernova, creating a hypernova that outshines 10 billion suns. This hypernova eruption happens when stars over 150 times more massive than our sun undergo core collapse while rotating at nearly breakup speeds. The combination of extreme mass and rapid rotation creates an explosion so violent that it launches material into space at speeds approaching the velocity of light itself. These stellar monsters burn through their nuclear fuels so rapidly that they live only a few million years before facing their catastrophic end. Hypernovas form when the most massive stars in the universe exhaust their nuclear fuel while spinning faster than a carnival ride. Picture a figure skater pulling in their arms to spin faster. Except this skater weighs 150 times more than our sun and rotates several times per second. The centrifugal force from this rotation stretches the collapsing core into an oblate shape and channels the explosion's energy into two narrow jets that burst from the star's poles. The core collapse phase proceeds similarly to normal supernovas, but with far more extreme conditions. When the stellar core reaches nuclear density, it rebounds and creates shock waves that propagate through over 100 solar masses of stellar material. The enormous gravitational binding energy of such massive stars means the explosion must overcome incredible resistance to blast apart the outer layers. What makes hypernovas truly extraordinary is their ability to accelerate material to relativistic speeds. The polar jets can reach velocities exceeding 99% the speed of light, creating narrow beams of ultra-hot plasma that punch through the star's outer layers like cosmic drill bits. These jets carry kinetic energies that exceed the total binding energy of normal stars. The explosion creates exotic conditions where matter and antimatter particles pop into existence from pure energy following Einstein's equation in reverse. Electron-positron pairs form and annihilate continuously in the intense radiation field, adding to the explosion's total energy output. Some hypernovas produce enough antimatter to power entire civilizations for millions of years if it could somehow be captured and stored. Hypernovas synthesize elements beyond iron in quantities that dwarf normal supernovas. The extreme neutron flux during the explosion drives rapid neutron capture processes that forge elements like gold, platinum, and uranium. A single hypernova can produce more heavy elements than dozens of regular supernovas combined. The most powerful hypernovas can be detected across distances exceeding 13 billion light years, allowing astronomers to observe these explosions from when the universe was less than 1 billion years old. These ancient hypernovas provide glimpses of the first generation of massive stars and help explain how heavy elements spread throughout the early cosmos. When hypernovas' jets break through the stellar surface, they continue propagating through space for thousands of years, creating some of the longest-lasting and most energetic phenomena in astronomy. However, these incredible stellar explosions are merely the opening act for even more devastating events that can flood entire sections of the universe with deadly radiation. A beam of gamma rays fires across 13 billion light-years of space with such concentrated energy that it could sterilize every planet within 6,000 light-years of its source. This gamma-ray burst releases more energy in 10 seconds than our sun will produce over its entire 10 billion-year lifetime, and it focuses this energy into a cone so narrow that it covers less than 1% of the sky. If a gamma-ray burst occurred in our galaxy and pointed toward Earth, it would strip away our ozone layer completely and trigger a mass extinction event that could end most life on our planet. Gamma-ray bursts represent the most energetic explosions in the universe since the Big Bang itself. They occur when massive stars collapse into black holes while rotating at extreme speeds, or when two neutron stars spiral into each other and merge. The resulting black hole launches jets of plasma at velocities exceeding 9% the speed of light, creating narrow beams of radiation that can travel across the entire observable universe. These cosmic death rays maintain their deadly intensity across unimaginable distances because they are so tightly collimated. Think of the difference between a flashlight and a laser pointer. A flashlight spreads its light in all directions and becomes dim quickly, but a laser focuses its energy into a narrow beam that can travel much farther while maintaining dangerous intensity levels. The gamma rays in these bursts carry individual photons with energies millions of times higher than visible light. Each photon packs enough energy to break chemical bonds and damage DNA directly. During the burst phase, which typically lasts between 2 seconds and 2 minutes, the gamma ray flux can exceed the brightness of the rest of the observable universe combined in this high-energy radiation band. Long-duration gamma ray bursts lasting more than 2 seconds originate from hypernovas in distant galaxies. The collapsing stellar core forms a rapidly spinning black hole surrounded by an accretion disk of infalling material. Magnetic field lines threading through this disk become twisted and wound up until they snap and reconnect, launching relativistic jets along the black hole's rotation axis, short-duration gamma ray bursts. Lasting less than 2 seconds come from neutron star mergers that we will explore shortly. These collisions create similar black hole and accretion disk systems, but with different compositions and energy scales. Both types of gamma-ray bursts can produce afterglows that remain detectable for weeks or months as the relativistic jets interact with surrounding material. The most powerful gamma-ray burst ever detected, known as GRB 08096c, occurred 5 billion light-years from Earth and was visible to the naked eye despite this enormous distance. For about 40 seconds, this single stellar explosion outshone every star and galaxy in our night sky, and could have been seen by human eyes alone if anyone had been looking in the right direction. Gamma-ray bursts provide natural laboratories for studying matter under the most extreme conditions possible. But even these universe-spanning death rays seem almost gentle compared to the cosmic catastrophes that occur when neutron stars themselves collide and forge the heaviest elements in nature through pure violence. Two neutron stars, each containing more mass than our sun compressed into a sphere the size of Manhattan, spiral into each other at half the speed of light and explode with the power of 100 million suns. This kilonova collision creates gravitational waves that ripple through the fabric of space-time itself, stretching and compressing the distance between atoms as the waves pass through Earth. The merger also forges more gold in a few seconds than our sun could produce if it somehow converted its entire mass into precious metals through nuclear alchemy. Kilonova events begin billions of years earlier when two massive stars in a binary system both explode as supernovas and leave behind neutron star remnants. These stellar corpses continue orbiting each other, but they gradually spiral inward as they lose energy by emitting gravitational waves. The process takes so long that the original binary system has usually been disrupted and flung through space before the final merger occurs. During the last few minutes before collision, the two neutron stars orbit each other hundreds of times per second while accelerating to incredible velocities. The gravitational forces become so intense that they tidally distort the neutron stars, pulling them into elongated shapes like cosmic teardrops. Material begins streaming between the two objects as their surfaces are literally torn apart by tidal forces. When the neutron stars finally touch, they merge in a catastrophic explosion that combines the mass of two entire stars into a single object in less than 1,000th of a second. The collision creates temperatures exceeding 1 billion degrees Fahrenheit and pressures so extreme that atomic nuclei are crushed together and forced to capture multiple neutrons in rapid succession. This rapid neutron capture process, called the R process, builds atomic nuclei much heavier than iron by adding neutrons faster than they can decay radioactively. Elements like gold, platinum, and uranium form through this process as neutron-rich nuclei capture dozens of additional neutrons before having time to beta decay into more stable configurations. The kilonova explosion ejects several Earth masses worth of neutron-rich material into space at speeds exceeding 10,000 miles per second. This ejected material glows with the heat of radioactive decay as the freshly synthesized heavy elements break down into more stable forms. The resulting light show can outshine entire galaxies for weeks and remains detectable for months. The August 17, 2017 kilonova detection marked the beginning of multi-messenger astronomy, where gravitational waves, electromagnetic radiation, and possibly neutrinos from the same cosmic event were observed simultaneously. This collision was detected by gravitational wave observatories on Earth just 1.7 seconds before satellites observed the resulting gamma-ray burst. Computer simulations suggest that kilonova collisions produce enough heavy elements to account for most of the gold, platinum, and uranium observed in the universe today. Every gold ring, platinum catalyst, and uranium fuel pellet contains atoms that were forged in the violent merger of neutron stars billions of years ago. However, even the incredible gravitational forces that drive kilonova collisions pale in comparison to what happens when gravity becomes so strong that not even light itself can escape from its grasp. When a star 100 times more massive than our sun collapses, gravity becomes so overwhelmingly powerful that it creates a region of space-time where the laws of physics break down completely. This stellar mass black hole formation tears a hole in the fabric of reality itself, creating an event horizon where time slows to a crawl and space becomes infinitely curved. The gravitational pull is so intense that anything crossing this boundary can never return to the outside universe, not even light moving at 671 million miles per hour. Black hole formation occurs when the core of a massive star collapses beyond the point where neutron degeneracy pressure can resist further compression. Unlike neutron star formation, where quantum forces eventually halt the collapse, nothing in the known universe can stop matter from falling inward once it passes the Schwarzschild radius. The collapsing core shrinks toward a mathematical point called a singularity, where density becomes infinite and the curvature of space-time becomes infinitely steep. The event horizon forms at the moment when the escape velocity from the collapsed core equals the speed of light. Think of throwing a ball upward from Earth's surface. If you throw it fast enough, it will escape Earth's gravity and never fall back down. But near a black hole, you would need to throw the ball at the speed of light for it to escape. And since nothing with mass can reach light speed, nothing can ever get away. During the collapse phase, the dying star's outer layers fall inward at speeds approaching 60,000 miles per second. As this material crosses the event horizon, it disappears from our universe forever. The gravitational binding energy released during this process can power some of the most luminous explosions in the cosmos, but most of the energy falls into the black hole and is lost to the outside world. Black holes warp space and time in ways that seem impossible according to our everyday experience. Time dilation effects become so extreme near the event horizon that if you could somehow survive watching someone fall into a black hole, you would see them slow down and freeze just before crossing the boundary. From their perspective, they would fall through normally, but their image would become redshifted and fade away as observed from outside. The tidal forces near stellar mass black holes can stretch objects into long, thin shapes in a process astronomers call spaghettification. These forces arise because gravity weakens with distance, so your feet would experience much stronger gravitational pull than your head if you fell feet first toward a black hole. The difference would literally tear you apart long before you reach the event horizon. Stellar mass black holes can form through direct collapse during supernova explosions or through the accretion of material onto neutron stars that pushes them beyond the maximum mass they can support. Once formed, these cosmic vacuum cleaners continue growing by consuming any matter that ventures too close to their gravitational influence. However, stellar mass black holes are cosmic lightweights compared to their intermediate-sized cousins that can devour entire star systems and reshape the architecture of galaxies through their gravitational influence. A black hole 1,000 times more massive than our sun tears apart an entire solar system, consuming planets, asteroids, and comets while converting 10% of their mass into pure energy. This intermediate black hole feeding event releases more power than 1 trillion nuclear weapons, detonating every single second for 1 million years. The accretion disk of superheated materials spiraling into the black hole reaches temperatures exceeding 100 million degrees Fahrenheit and outshines entire star clusters with its brilliant X-ray emissions. Intermediate mass black holes occupy the mysterious middle ground between stellar mass black holes and the supermassive monsters that lurk at galaxy centers. With masses ranging from 100 to 100,000 times our sun, these cosmic predators are large enough to swallow entire solar systems, but small enough to wander through galaxies like gravitational nomads seeking their next meal. When an intermediate black hole encounters a star system, its immense gravitational field disrupts planetary orbits and sends worlds spiraling toward destruction. The process begins subtly as the black hole's gravity perturbs the outer planets, gradually destabilizing their orbits over thousands of years. Eventually, these worlds are either ejected into interstellar space or pulled inward toward the black hole itself. As material falls toward an intermediate black hole, it forms an accretion disk where gravitational potential energy converts to thermal energy through friction and magnetic interactions. The inner regions of this disk reach temperatures hot enough to ionize any atoms completely, creating a plasma so energetic that electrons are stripped away from atomic nuclei and accelerated to relativistic speeds. The feeding process creates jets of high-energy particles that stream away from the black hole's poles at nearly the speed of light. These jets can extend for hundreds of light years and punch through the surrounding interstellar medium like cosmic blowtorches. The magnetic fields threading through the accretion disk become twisted and amplified until they snap and reconnect violently, launching these particle beams into space. Intermediate black holes can consume matter so efficiently that they convert approximately 10% of the infalling mass directly into energy, according to Einstein's famous equation. This makes them among the most efficient energy sources in the universe, far more effective than nuclear fusion or even matter-antimatter annihilation for extracting energy from mass. During active feeding phases, intermediate black holes become some of the most luminous objects in their local regions of space. They can outshine the combined light of millions of stars and remain visible across distances of billions of light years. The X-ray emissions from their accretion disks are so intense they can be detected by space-based telescopes throughout the observable universe. Some intermediate black holes form through the merger of multiple stellar mass black holes in dense star clusters. Others may be the remnants of the first generation of supermassive stars that existed in the early universe. These primordial black holes could have formed when the cosmos was less than 1 billion years old and been wandering through space ever since. But intermediate black holes are merely stepping stones toward the ultimate gravitational monsters that anchor entire galaxies and launch plasma jets extending across millions of light years of space. A black hole 4 billion times more massive than our sun launches twin jets of plasma that extend for 5 million light years, carrying enough energy to heat intergalactic space and prevent new stars from forming across vast regions of the universe. These supermassive black holes move at 99.5% the speed of light and maintain their coherent structure across distances that dwarf individual galaxies. The jets from the galaxy Messier 87 carry more power than 10 trillion suns and have been actively flowing for over 100 million years without showing any signs of weakening. Supermassive black hole jets form when matter spirals into black holes that contain millions or billions of times the mass of our sun. The accretion disk around such massive objects generates magnetic fields so powerful they can channel infalling material into narrow beams that shoot out from the black hole's poles like cosmic fire hoses. These magnetic field lines become twisted and wound up by the rotation of the accretion disk until they snap and launch material outward at nearly light speed. The jets remain collimated across enormous distances through a process that still puzzles astrophysicists. Think of trying to maintain a tight stream of water from a garden hose while spraying it across your entire neighborhood. The jets somehow resist spreading out even as they traverse distances equivalent to the separation between our galaxy and its nearest large neighbor. When these relativistic jets encounter the thin gas that fills the space between galaxies, they create enormous bubbles of hot plasma that can span millions of light years. The galaxy Perseus A has blown 2 such bubbles that together could contain thousands of galaxies the size of our Milky Way. The energy required to create these cosmic cavities exceeds the total binding energy of entire galaxy clusters. Supermassive black hole jets can actually regulate star formation across entire galaxies by heating the surrounding gas to temperatures that prevent gravitational collapse. This process, called AGM feedback, helps explain why the most massive galaxies in the universe contain relatively few young stars, despite having enough raw material to form billions of additional stellar systems. Some jets proceed at such high speeds that they create shockwaves in space itself as they plow through the intergalactic medium. These cosmic sonic booms heat gas to hundreds of millions of degrees and accelerate particles to energies that exceed those produced in our most powerful particle accelerators by factors of millions. The most powerful jets can be detected across distances exceeding 13 billion light years, allowing astronomers to observe supermassive black holes that were active when the universe was less than 1 billion years old. These ancient monsters help us understand how the first galaxies formed and evolved during the cosmic dark ages. Radio telescopes can trace supermassive black hole jets across the entire electromagnetic spectrum, from low-frequency radio waves to high-energy gamma rays. The jets emit synchrotron radiation as relativistic electrons spiral around magnetic field lines, creating some of the brightest radio sources in the observable universe. Yet even these galaxies spanning plasma streams pale in comparison to what happens when entire galaxies themselves crash into each other with enough gravitational force to trigger the most spectacular cosmic collisions imaginable. Two spiral galaxies, each containing over 100 billion stars, slam into each other at speeds exceeding 1 million miles per hour in a cosmic collision that will reshape both systems over the next 5 billion years. This galaxy merger releases gravitational binding energy equivalent to the combined light output of both galaxies for over 1 billion years. The collision triggers massive bursts of star formation as gas clouds crash together and compress, creating new stellar nurseries that can form stars at rates hundreds of times faster than normal galactic processes. Galaxy collisions begin billions of years before the actual merger, as the two systems approach each other through their mutual gravitational attraction. Long before they physically overlap, tidal forces start distorting both galaxies and pulling out enormous streams of stars that can extend for hundreds of thousands of light years. These stellar streams create spectacular bridges and tails that trace the gravitational dance between the merging systems. When galaxies finally interpenetrate each other, individual stars rarely collide directly because the spaces between them are so vast. Think of two swarms of gnats flying through each other, where the gnats represent stars, and the empty space between them dominates the interaction. However, the gravitational effects are profound as stars get flung into new orbits, and the overall structure of both galaxies becomes completely scrambled. The supermassive black holes at the centers of both galaxies begin a deadly spiral dance as they lose energy through gravitational wave emission. This black hole merger can release more energy in gravitational waves than all the stars in both galaxies combined produce an electromagnetic radiation. The final coalescence creates gravitational wave bursts so powerful they can be detected by instruments on Earth even when the merger occurs billions of light years away. During the most violent phases of galaxy collision, star formation rates can increase by factors of 100 or more as giant molecular clouds crash together and fragment into dense stellar nurseries. These starburst episodes create massive young stars that burn brightly, but die quickly in supernova explosions, enriching the surrounding gas with heavy elements and triggering additional waves of star formation. Some galaxy mergers completely disrupt one or both of the original systems, scattering stars across millions of light years and creating diffuse stellar halos around the merger remnant. Other collisions result in the formation of giant elliptical galaxies that contain the combined mass of both progenitor systems, but have lost most of their original spiral structure. The Milky Way is currently on a collision course with the Andromeda Galaxy, and this merger will begin in approximately 4.5 billion years. Computer simulations suggest our solar system will likely survive the collision and end up in the outer regions of the resulting elliptical galaxy, which astronomers have nicknamed Milkomeda. Galaxy groups and clusters contain hundreds or thousands of galaxies that interact gravitationally over cosmic timescales. These environments host multiple galaxy mergers simultaneously, creating some of the most complex and energetic processes in the observable universe. However, galaxy collisions represent just the beginning of truly cosmic scale violence, as the supermassive black holes they create can become the brightest and most energetic objects in the entire universe. A supermassive black hole 10 billion times more massive than our sun devours matter so rapidly that it outshines 1 trillion stars and becomes visible from the edge of the observable universe. This quasar activity converts infalling material into pure energy with such incredible efficiency that the accretion disk around the black hole glows brighter than entire galaxy clusters containing thousands of individual galaxies. The energy output exceeds our sun's luminosity by factors of 10 trillion, making quasars the most luminous, continuously powered objects known to exist. Quasars form when supermassive black holes enter periods of extremely active feeding, often triggered by galaxy mergers that funnel enormous amounts of gas and dust toward the central black hole. The material forms a massive accretion disk that can extend for light years around the black hole, with the inner regions heated to temperatures exceeding 1 million degrees Fahrenheit through friction and magnetic interactions. The name quasar comes from quasi-stellar radio source, because these objects initially appeared as point-like sources in early radio telescopes. However, their enormous distances mean that quasars must be incredibly luminous to appear as bright as they do from Earth. The closest quasar lies over 2 billion light-years away, yet it can be observed with modest amateur telescopes. During peak activity phases, quasars can consume material at rates exceeding 1 solar mass per year. This means the supermassive black hole is literally eating the equivalent of our entire sun every 12 months, while converting approximately 10% of this matter directly into energy. The resulting luminosity can fluctuate dramatically over time scales ranging from hours to decades as the feeding rate varies. The most powerful quasars generate winds and outflows that can clear gas from their host galaxies completely, effectively shutting down star formation across the entire system. These galactic-scale winds move at speeds exceeding 10,000 miles per second and carry away material with enough energy to unbind entire galaxy clusters if directed properly. Some quasars exhibit broad absorption lines in their spectra, indicating that material is flowing away from the central black hole at significant fractions of the speed of light. These broad absorption line quasars may represent a special evolutionary phase where the supermassive black hole is in the process of clearing away its surrounding material and transitioning to a less active state. The most distant quasars observed formed when the universe was less than 1 billion years old, suggesting that supermassive black holes with billions of solar masses existed much earlier in cosmic history than previously thought possible. These ancient quasars challenge our understanding of how such massive black holes could grow so quickly in the early universe. Quasar variability provides insights into the structure and physics of accretion disks around supermassive black holes. Some quasars change brightness by factors of 10 or more over periods of months, indicating that the energy production regions are surprisingly compact given the enormous masses involved. However, quasar activity represents just one manifestation of supermassive black hole feeding. And there are even more extreme cases where these cosmic monsters consume entire solar systems while generating the most powerful sustained energy sources in the known universe. A supermassive black hole at the center of a galaxy tears apart and devours an entire solar system every few days, while launching relativistic jets that sterilize planets across thousands of light years with deadly radiation. This active galactic nucleus operates like a cosmic meat grinder that can process the mass equivalent of our entire solar system in less than a week. The supermassive black hole's accretion disk becomes so luminous that it outshines all 400 billion stars in its host galaxy combined, creating a beacon of destruction visible across most of the observable universe. Active galactic nuclei represent the most extreme feeding modes of supermassive black holes encompassing quasars, blazars, seafront galaxies, and radio galaxies. Each type exhibits different characteristics depending on the viewing angle, accretion rate, and jet orientation, but all share the common feature of central black holes consuming matter at prodigious rates while converting it into electromagnetic radiation and relativistic particle beams. The feeding process begins when stars, gas clouds, or even entire planetary systems venture too close to the supermassive black hole's gravitational influence. Tidal forces stretch and tear apart these objects long before they reach the event horizon, heating the debris to millions of degrees as it spirals inward through the accretion disk. The inner regions of this disk reach temperatures exceeding 1 billion degrees Fahrenheit, hot enough to emit high-energy X-rays and gamma rays. Blazars represent the most extreme class of active galactic nuclei, where relativistic jets point directly toward Earth and create some of the most violent and rapidly varying phenomena in astronomy. These cosmic lighthouses can change brightness by factors of 100 or more in just a few hours, as relativistic effects amplify their emission through Doppler boosting and relativistic beaming. The most powerful active galactic nuclei generate enough energy to heat the entire intergalactic medium within their galaxy clusters, preventing new galaxies from forming and regulating the growth of existing systems. This feedback process helps explain why the most massive galaxies in the universe appear to have stopped forming new stars despite containing enormous reservoirs of gas and dust. Some active galactic nuclei exhibit periodic outbursts that repeat every few years or decades as material falls into the central black hole in distinct episodes. These quasi-periodic oscillations may result from the disruption of large gas clouds or the partial tidal stripping of stars that pass close to the black hole but manage to escape complete destruction. Radio-loud active galactic nuclei produce jets that can extend from millions of light years and create enormous radio lobes filled with relativistic plasma. These structures represent some of the largest coherent objects in the universe and can influence star formation and gas dynamics across entire galaxy clusters. The study of active galactic nuclei provides crucial insights into black hole physics, accretion disk dynamics, and jet formation mechanisms. However, these supermassive feeding frenzies are just one way that the universe accelerates particles to incredible energies that challenge our understanding of fundamental physics. Individual protons race through space at 99.9999% the speed of light, carrying more energy than a professional baseball thrown at 60 miles per hour despite being trillions of times smaller than a single atom. These ultra-high energy cosmic rays possess energies exceeding 10 to the 20th electron volts, which is over 100 million times more powerful than anything achieved in our most advanced particle accelerators. A single cosmic ray proton carries enough kinetic energy to lift a paperclip off a desk, concentrated into a space smaller than the nucleus of an atom. Cosmic ray acceleration occurs through a variety of violent astrophysical processes, including supernova shock waves, active galactic nuclei, gamma-ray bursts, and neutron star magnetosphere. These cosmic particle accelerators operate on scales and energies that dwarf anything possible with human technology, creating natural laboratories for studying matter under the most extreme conditions imaginable. The highest energy cosmic rays originate from sources beyond our galaxy, possibly from the jets of active galactic nuclei or the shock waves created by galaxy cluster mergers. These extragalactic particles must overcome the cosmic microwave background radiation that fills all of space, which acts like a headwind that saps energy from ultra-relativistic particles through interactions with background photons. When ultra-high energy cosmic rays strike Earth's atmosphere, they create extensive air showers containing billions of secondary particles that spread across areas larger than major cities. The primary cosmic ray proton collides with an atmospheric nucleus and fragments into dozens of secondary particles, which then collide with other nuclei and create even more particles in a cascading chain reaction that can extend for miles through the atmosphere. The most energetic cosmic ray ever detected carried an energy of 3 times 10 to the 20th electron volts and was nicknamed the "Oh my God" particle by the scientists who discovered it. This single proton possessed about the same kinetic energy as a baseball thrown at 60 miles per hour, but compressed into a space billions of times smaller than the period at the end of this sentence. Cosmic ray acceleration mechanisms remain one of the greatest unsolved mysteries in astrophysics. The energies involved require magnetic fields and shock waves operating over vast distances and timescales. Supernova remnants can accelerate particles through Fermi acceleration, where charged particles bounce back and forth across moving shock fronts and gain energy with each collision. Some cosmic rays may be accelerated in the magnetospheres of rapidly rotating neutron stars, where particles can surf on electromagnetic waves and reach enormous energies before being launched into interstellar space. Others might gain energy through magnetic reconnection events in the vicinity of supermassive black holes or during the merger of neutron stars. The study of cosmic rays provides unique insights into the most energetic processes in the universe and helps astronomers understand how matter behaves under conditions that cannot be reproduced in terrestrial laboratories. These particles serve as messengers from the most violent regions of space, carrying information about distant cosmic accelerators across billions of light years. Yet cosmic rays represent just individual particles racing through a universe dominated by invisible forces that operate on scales so vast they shape the entire cosmic web of matter and energy. And invisible scaffolding of dark matter spanning billions of light years orchestrates the formation of every galaxy, star, and planet in the observable universe through gravitational forces that dwarf all other cosmic influences combined. This dark matter network contains 5 times more mass than all the normal matter we can see, creating a cosmic web of filaments and nodes that guides the flow of gas and the birth of galaxies across 13.8 billion years of cosmic evolution. The gravitational binding energy stored in dark matter structures exceeds the total energy output of every star that has ever existed. Dark matter interactions occur primarily through gravitational attraction, but these effects operate on such enormous scales that they control the large-scale structure of the entire universe. Dark matter particles stream through space at speeds exceeding 600 miles per second, creating vast halos around galaxies that extend far beyond the visible edges of stellar systems. During the early universe, tiny fluctuations in dark matter density grew through gravitational instability into the massive structures we observe today. These primordial seeds attracted normal matter and eventually led to the formation of the first stars and galaxies. Without dark matter's gravitational scaffolding, the universe would have remained a nearly uniform sea of hydrogen and helium gas with no stars, planets, or life. Galaxy clusters represent the largest gravitationally bound structures in the universe, containing thousands of individual galaxies held together primarily by dark matter gravity. The dark matter halos in these clusters contain more mass than 10,000 galaxies, like our Milky Way, creating gravitational fields so powerful they bend light from background objects and act like cosmic magnifying glasses. When dark matter halos collide during galaxy cluster mergers, they can separate from the normal matter and continue moving independently. The bullet cluster collision demonstrates this effect dramatically, showing dark matter halos that have passed through each other while the normal matter remains behind in hot X-ray emitting gas clouds heated by the collision. Direct detection experiments deep underground search for dark matter particles passing through Earth, but these elusive particles interact so weakly with normal matter that billions pass through your body every second without leaving any trace. The total dark matter density in our solar system exceeds the mass of a small asteroid, yet it has no measurable effect on planetary orbits because it is spread so diffusely through space. Numerical simulations of dark matter evolution predict the formation of vast cosmic web structures with dense nodes connected by filamentary bridges spanning hundreds of millions of light years. Normal matter follows this dark matter scaffolding, creating the observed distribution of galaxies and galaxy clusters throughout the observable universe. Some theories suggest dark matter may interact through forces other than gravity, potentially leading to dark matter annihilation events that could produce high-energy gamma rays or exotic particles. These hypothetical interactions might create some of the most energetic phenomena in the universe while remaining completely invisible to electromagnetic observation. However, even the vast gravitational forces of dark matter pale in comparison to theoretical processes that could literally destroy the fundamental structure of reality itself and unravel the fabric of space and time. A bubble of true vacuum begins expanding at the speed of light and destroys everything in its path by rewriting the fundamental laws of physics and making atoms, molecules, and life itself impossible to exist. This vacuum decay event would release more energy per unit volume than any other process in theoretical physics, effectively erasing the universe as we know it and replacing it with a reality where matter cannot form stable structures. The expanding bubble would be completely invisible and unstoppable, arriving without warning and annihilating everything instantaneously. Vacuum decay could occur if our universe exists in a false vacuum state, meaning the quantum fields that fill all of space are not actually in their lowest possible energy configuration. Think of a ball balanced on top of a hill instead of resting in the valley below. The ball appears stable, but if it gets pushed slightly, it will roll down to the true lowest point and release enormous amounts of energy. The Higgs field, which gives mass to fundamental particles, might exist in such a false vacuum state. If quantum fluctuations or high-energy particle interactions cause the Higgs field to tunnel to a lower energy state somewhere in space, this change would spread outward at light speed in an expanding sphere of destruction. Inside this bubble, the laws of physics would be completely different and incompatible with the existence of atoms. Vacuum decay would be absolutely catastrophic because it would change the fundamental constants that govern how particles interact with each other. Electrons might not be able to orbit atomic nuclei, or the strong nuclear force might become too weak to hold protons and neutrons together inside atomic nuclei. Any matter caught in the expanding bubble would instantly disintegrate into its component particles. The energy released during vacuum decay comes from the difference between the false vacuum and true vacuum energy densities. This energy difference might seem small when expressed per unit volume, but when multiplied by the volume of the entire observable universe, it represents an amount of energy that exceeds the binding energy of every atom, molecule, and structure that has ever existed. Current calculations suggest our universe might be metastable, meaning vacuum decay is theoretically possible, but extremely unlikely to occur naturally. However, sufficiently energetic particle collisions or the formation of microscopic black holes might trigger vacuum tunneling events that could initiate the decay process. If vacuum decay began somewhere in our galaxy, we would have no warning of its approach, because the destruction bubble moves at light speed. There would be no way to detect it, escape from it, or protect against it. The expanding sphere would simply erase everything in its path and continue growing until it consumed the entire observable universe. Some theoretical physicists have proposed that vacuum decay might have already occurred elsewhere in the universe, but the destruction bubbles have not yet reached us due to the vast distances involved and the finite age of the cosmos. These bubbles might be expanding toward us right now, invisible and unstoppable. Yet even this ultimate destruction pales in comparison to the creative forces that originally brought our universe into existence, through processes so violent they make vacuum decay seem gentle by comparison. 3 minutes after the Big Bang, the entire observable universe became a cosmic nuclear reactor, operating at temperatures exceeding 1 billion degrees Fahrenheit, and forging the first atomic nuclei from primordial energy in matter. This Big Bang nucleosynthesis process converted nearly 25% of all protons in the universe into helium nuclei, while the cosmos was still hot and dense enough to sustain nuclear fusion on a scale that dwarfs every star has ever existed or ever will exist. The energy densities during this epoch exceeded anything achievable in terrestrial laboratories by factors of trillions. Big Bang nucleosynthesis began when the universe cooled enough for protons and neutrons to survive without being immediately destroyed by high-energy photons. During the first few minutes of cosmic history, the entire universe was hotter and denser than the core of the most massive stars, creating conditions where nuclear fusion could occur everywhere simultaneously. The process started with a fusion of protons and neutrons to form deuterium, a heavy isotope of hydrogen containing 1 proton and 1 neutron. This reaction required the universe to cool below about 1 billion degrees, because at higher temperatures, the abundant high-energy photons would immediately break apart any deuterium nuclei that form. This temperature threshold created a brief window when nuclear fusion could proceed rapidly throughout the cosmos. Once deuterium became stable, it quickly fused with additional protons and neutrons to form helium for nuclei, each containing 2 protons and 2 neutrons. This process was so efficient that nearly all available neutrons ended up incorporated into helium nuclei within just a few minutes. The nuclear binding energy released during this cosmic fusion episode helped drive the expansion of the universe itself. Big Bang nucleosynthesis also produced smaller amounts of helium-3, lithium-7, and trace quantities of other light elements. However, the expansion and cooling of the universe prevented the formation of heavier elements, because the nuclear reactions required increasingly higher temperatures and densities that could no longer be sustained as the cosmos diluted. The relative abundances of light elements produced during Big Bang nucleosynthesis provide some of the strongest evidence for the Big Bang theory itself. Observations of primordial helium and deuterium in the most ancient gas clouds match theoretical predictions with remarkable precision, confirming our understanding of conditions during the first few minutes of cosmic history. The neutron-to-proton ratio during nucleosynthesis was determined by the fundamental constants of particle physics and the expansion rate of the early universe. This ratio controlled how much helium formed relative to hydrogen, and the observed helium abundance allows cosmologists to constrain models of the very early universe and test theories of fundamental physics. Big Bang nucleosynthesis represents the first time in cosmic history when matter began assembling into stable structures more complex than individual particles. This primordial nuclear fusion created the raw materials that would eventually enable star formation, planet formation, and the emergence of life billions of years later. However, nucleosynthesis was just one consequence of an even more dramatic process that occurred during the universe's first moments when space itself expanded faster than light and created everything we can observe today. During the first tiny fraction of a second after the Big Bang, space expanded faster than the speed of light and inflated a region smaller than an atomic nucleus to larger than a grapefruit in less time than it takes light to cross a proton. This cosmic inflation process increased the size of the universe by a factor of at least 10 to the 26th power, which means a region that originally measured 1/1,000,000th of a trillionth of an inch suddenly became larger than a basketball. The expansion happened so rapidly that it violated Einstein's speed limit for matter and energy while remaining consistent with general relativity. Cosmic inflation was driven by a hypothetical energy field called the inflaton that filled all of space during the universe's earliest moments. This field possessed the remarkable property of negative pressure, which caused space itself to expand exponentially while the field maintained nearly constant energy density. Think of a substance that creates more of itself as it stretches, providing the energy needed to drive continued expansion. The inflationary expansion stretched quantum fluctuations in the inflaton field from subatomic scales to cosmic dimensions, creating the tiny density variations that would eventually grow into galaxies, stars, and planets. These quantum ripples in space-time represent the smallest possible fluctuations allowed by the uncertainty principle, magnified to cosmic proportions by the violent expansion of space itself. Inflation solved several major cosmological puzzles, including why the universe appears so uniform in temperature and density across vast regions that should never have been in causal contact. The cosmic microwave background radiation shows temperature variations of only 1 part in 100,000 across the entire sky, indicating that widely separated regions of space were once close enough together to reach thermal equilibrium. The energy scale during inflation was approximately 10 to the 16th billion electron volts, which exceeds the energies achievable in particle accelerators by factors of trillions. This enormous energy density approached the Planck scale, where quantum effects of gravity become important and our current understanding of physics breaks down completely. Inflation ended when the inflaton field rolled down from its high energy state to a lower energy minimum, converting its enormous energy into the hot, dense soup of particles and radiation that we call the Big Bang. This process, called reheating, created all the matter and energy in the observable universe from the vacuum energy stored in the inflaton field. Some theories suggest that inflation may still be occurring in regions of space beyond our observable universe, continuously creating new pocket universes with different physical laws and constants. This eternal inflation scenario implies that our universe is just one bubble in an infinite multiverse where every possible combination of physical laws exists somewhere. The rapid expansion during inflation stretched space so dramatically that most of the universe lies beyond our cosmic horizon and will never be observable no matter how long we wait or how powerful our telescopes become. We can only see the tiny fraction of creation that lies within our observable bubble. Yet inflation itself emerged from an even more mysterious and powerful singularity, where all known physics breaks down and space, time, matter, and energy emerged from literally nothing at all. At the very beginning of time, space, matter, and energy exploded into existence from a mathematical point of infinite density and infinite temperature, where the laws of physics cease to have meaning. This Big Bang singularity represents the ultimate source of all power in the universe, creating everything we observe in quantum vacuum fluctuations that somehow transcended the boundary between nothing and something. The energy density at the moment of creation exceeded any finite number you could possibly imagine, concentrated into a space smaller than the smallest measurable distance in physics. The Big Bang singularity defies human comprehension because it exists beyond the realm where our scientific theories can provide meaningful descriptions. At temperatures exceeding 10 to the 32nd power degrees Fahrenheit and densities approaching infinity, the fundamental forces that govern reality merge into a single unified interaction that we cannot yet understand or describe mathematically. During the Planck epoch, the first 10 to the minus 43 seconds of cosmic history, space and time themselves became quantum mechanical and subject to uncertainty principles. At this scale, the fabric of space-time dissolved into a foaming sea of virtual particles and quantum geometries where the very concepts of before and after lose their meaning. The Big Bang created not just matter and energy, but the dimensions of space and time that contained everything we experience. There was no space for the universe to expand into and no time before the beginning, because space and time themselves came into existence along with everything else. The entire framework of reality emerged from this singular moment of infinite creative power. What triggered the Big Bang remains the deepest mystery in science. Some theories suggest it resulted from quantum fluctuations in a pre-existing multiverse, while others propose it arose spontaneously from nothing through processes we cannot yet comprehend. The total energy of the universe might actually be zero, with positive matter energy balanced by negative gravitational potential energy, making creation possible without violating conservation laws. The Big Bang singularity possessed infinite creative potential because it contained all possible futures in quantum superposition. Every particle that would ever exist, every star that would ever shine, every planet that would ever form, and every thought that would ever be conceived existed as probability waves in the quantum foam of that first moment. As the universe emerged from the singularity and began expanding, it passed through phase transitions that broke the fundamental symmetries of nature and gave rise to the four forces we observed today. The electromagnetic force, the weak nuclear force, the strong nuclear force, and gravity all emerged as distinct interactions as the cosmos cooled and space-time crystallized into the reality we inhabit. The Big Bang singularity represents the absolute limit of power because it created everything from nothing, establishing the very foundation upon which all other energetic processes operate. Every lightning bolts, every supernova, every galaxy collision, and every black hole merger ultimately traces its energy back to that first moment when infinite potential became finite reality. In the end, the most powerful thing in the universe is the singularity that gave birth to the universe itself, creating space and time and matter and energy from the purest expression of creative force that will forever remain beyond our complete